Hello everyone, welcome to my channel. And guess who's here? It's my idol, Electronzap. Oh, what we have here? Oh, we have two circuits here. Let us see the two circuits here, built by my friend. What is this two circuit? It has a LED, a resistor, and a capacitor. This one, LED resistor capacitor. I think it's identical. What's the meaning of this? Are you kidding me, guys? Oh, difference is the capacitor. No, it's the same. I think the resistor is standing here. This one is in horizontal. But let us see the circuit diagram to tell what's the difference of the two. But here we are trying to build a capacitor circuit, and let's check the diagram here. So the diagram of this one is this capacitor circuit parallel. This is our new project circuit. We have a voltage supply, 12 volts, single pole, single throw switch, and we have this capacitor, a resistor, and an LED grounded. Just like that. And the circuit of this one is this. What is the circuit of this one? It's a capacitor circuit series. Project title. We have double supply, a switch, and a capacitor in series, a resistor, and LED. In here, the capacitor is in parallel with an LED. And this one, my previous circuit, previous circuit of my friend. Capacitor is in series with an LED. And we already calculated it, but let's review the current flow here with this old project, previous circuit. 12 volt supply, closing the switch, current flows to the capacitor. Upon closing the switch, capacitor charge, and while the capacitor is charging, I'm using 1000 microfarad, 16 volts capacitor, bigger than the supply. Don't use much smaller, it will destroy all the circuits here. While it's charging, still the current flows at the resistor here and an LED here, and it will light for a short period of time while still the capacitor is charging. I computed the value of the resistor here to protect my LED, just like that. We now know how to find the value of the resistor because this is my previous project. And we got here using Kirchhoff's voltage law and Ohm's law. And we got 500 ohms, the value of the resistor here. Just like that. Oh, I forgot my magic stick here. And time constant is computed this way. Resistor, capacitor, multiply the two and it becomes 0.5 seconds. That is the time constant while the capacitor is charging. Applied time constant will make the capacitor to attain this full charge of 99.3%. So we now know the parts here, a given, and the layout of this one. Let us see, what is this? This is the time constant. Pied time constant will charge a capacitor value of 99.3. Fully charged capacitor is 5 time constant here. So that's the operation of this circuit. My previous circuit. Let us see our new circuit here. Build by my friend. Capacitor circuit parallel. We have given here capacitor the same as the previous circuit, and the current at the LED is given data sheet here. It is given voltage supply of 12 volts. Let us see the current flow here. Closing the switch, current flows into the resistor. Capacitor, charging the capacitor, on and on, just like that. And also current flows here to the resistor and to the LED. Once the capacitor is fully charged, both have the same voltage level, 12 volts here, also 12 volts here. The difference of the two, potential difference is 0. So it means the LED will still turning on here. And we computed the value of the LED, the value of the resistor in the LED by using Kirchhoff's voltage law and my technique, sign technique, with negative voltage supply plus voltage of the resistor at the LED plus to negative, and then we have this 10 volts voltage drop across the resistor here. And this one, using Ohm's law, we have B is equals to IR. RD now is equal to 500 ohms, just like the previous project here. The same calculation, the same time constant here. Okay, let us see how to compute this time constant, just like that. Capacitor is charging here, and we have a time constant of 500 ohms times 100 microfarad. 500 times 1000 times 10 to the negative 6 is the same as microfarad here. And we have 5000, 1000, and 10 to the negative 6 is also equal to 0.00001. Just move it the 0 into 6 decimal point here, and we have a time constant of 0.5 seconds. To fully charge the capacitor, we need the 5 time constant here. Symbol this is tau, or 5 RC, which is 5 times 0.5, 2.5 seconds. So it takes 2.5 seconds to fully charge this capacitor connected in series or in parallel. Unlike here, this is in series. We get now here, and this is also our time constant table, voltage level. Fully charged 99.3% by using 5 RC, 5 times the time constant. And the remaining 0.7 is still in the circuit, circulating. 0.7, the current. 0.7, we cannot achieve 100% because there's still 0.7% in the circuit. That is the current flow while it is still connected into the circuit. So we have here the layout, the capacitor, LED, resistor, and we have now the parts here: capacitor, resistor, LED, breadboard. LED here is blue, and voltage supply is 12 volts. What's new here? When the capacitor is fully charged, still the LED is turning on. Unlike here, when the capacitor is fully charged, making a circuit open, the LED turns off. So that is the effect of connecting a capacitor in a series. just like that. And this one, connecting it in parallel, will just charging the capacitor, and still a little resistor value here, but it's negligible. While charging it, still the LED turns on. Let us see the circuit here. Wow, the circuit of this one is this one. And let us first see the circuit, my old circuit here. Okay, let's close the circuit. Pushing the switch. Oh, it means that the capacitor is fully charged, about 2.5 seconds. But the LED is now turning on. When it's fully charged, LED turns on, making this an open circuit here. There's no current flows here. LED turns on because the capacitor here is fully charged. Here, when you turn on the switch, it's still lighting. Why? Because the current flows here, charging the capacitor. When fully charged, still the LED turns on because the current pulse flows here also. So it can discharge here. It means we have two supply voltage here, but supplying here, the supply voltage is supplying a charge here, a current flows here, storing the charge, and also supplying a current here, some voltage here, current flows here and here. Also, it is just like having a water tank storage of the voltage or the charge. Both are supplying here in the LED, so it's still turned on. So the circuit flows like this. See, that is the operation of the capacitor in parallel. So we now know this one is still lighting on. This one, the LED is turned on because the capacitor is charged, fully charged here, making LED to turn on. Because of this capacitor, it becomes open here. So closing the circuit is slowly discharging. Why? Because the capacitor here is now supplying the current here when you open the switch until it becomes dark or no current flows. Unlike here, just blocking the LED from turning on. Okay, that's the operation of our capacitor circuit in series and in parallel. Thank you for watching the video, and bye.